In exercises 17 to 38, use the vertex and intercepts to sketch the graph of each quadratic function. Give the equation of the parabola as axis of symmetry and use the graph to determine the function's domain and range. So use the vertex and intercepts. Let's write 21 as y equals x minus 3 squared plus 1. So the vertex is 3, 1. So 3 and 1. To sketch the graph, give the equation. Well, the A, what's in front here, is 1. So that means it opens up and it hasn't been stretched or shrunk. So over 2 up, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. And we can go up here. It just fits for 3 over from the vertex. So there's the graph. Intercepts, use the vertex and intercepts. Give the equation of the parabola's axis of symmetry. So number 21, axis of symmetry is x equals 3. I could rather just put it down here, I guess, like that. Use the graph to determine the function's domain and range. The domain is negative infinity to infinity, and the range is 1 to infinity. So let's look at number 38. So negative b over 2a is the x-coordinate of the vertex, which is 4 over 2 times 1, so 2. So 2 comma something. Let's plug 2 in there. 6 minus 8 plus 4, so negative 2 plus 4 is 2. So 2, 2, 2, 2 is the vertex. So that's right there. A is positive 1, so again, it's just like x squared. So over 2, 1, 2, 3, 4, over 2 up 4, 1, 2, 3, 4, and we're not going to quite fit over 3 and up 9, but there it is. Give the equation of the parabola's axis of symmetry. Well, x is equal to is the axis of symmetry, and use the graph to determine the function's domain and range. So the domain is negative infinity to infinity, and the range is 2 to infinity. In exercise 45 to 48, give the domain and the range of each quadratic function whose graph is described. The vertex is negative 4, negative 6, and the parabola opens up. So that's going to be negative 4, negative 6. Give the domain and range. Well, the domain of a parabola that opens up or down is negative infinity to infinity, and the range is, if it opens up, it's from negative 6 to infinity is the range. The vertex is negative 2, 1 and opens down. So the domain is negative infinity to infinity, and the range is from negative infinity up to the y value, which is 1. In exercises 53 to 56, write an equation in standard form of the parabola that has the same shape as the graph of f of x equals 3x squared, or, so it opens up, or a parabola that opens down, but with the given maximum or minimum. So if it has a maximum of negative 4 at x equals 3, the vertex is 3, negative 4, and the parabola opens down. So we're going to use this one right here. So g of x is equal to negative 3, and we moved right 3 from 0, 0. So 0, 0 is over here, so we went right 3 and down 4. So right 3 and down 4. An athlete whose event is the shot put releases the shot with the same initial velocity but at different angles. The figure shows the parabolic paths for shots released at angles of 35 degrees and 65 degrees. Exercises 57 to 58 are based on the functions that model the parabolic paths. So 57, when the shot whose path is shown by the blue graph is released at an angle of 35 degrees, its height f of x in feet can be modeled by, so this is height after a certain distance. Where x is the shot's horizontal distance in feet from its point of release, use this model to solve parts A through C and verify your answer using the blue graph. What is the maximum height of the shot and how far from its point of release does this occur? Well, there's the maximum height. So we're looking at, possibly, I don't know, if you're given a graph, we're going to have to guess. But if we put this into a calculator, we'll know. And here off to the right, I've put this into Y1 already. So I'm going to turn off Y2. Let's graph this and see how close we are. We're not very close, by the way. So I noticed that if I look at their graph, the X goes all the way to 80 and the Y is going to 20. So 0 to, I better go to 80. We can go by tens. And then we're going from 0 to the highest. 20 will be higher than the highest. We can go by twos or tens or whatever. All right, so we're going to graph it. Now we want that maximum, don't we? What is the maximum height of the shot put, and when does that occur, in other words? So we're going to calculate the maximum. And let's go to the left here. Let's go to the right of the maximum. And we don't have to back up very far. That's probably good right there. So the height is actually 18.35. So 18.35, and we're measuring in feet. And it says, what is the maximum height of the shot and how far from its point of release does this occur? So 18 feet high and 35 feet away. We should answer it something like that. What is it? Excuse me. What is the shot's maximum horizontal distance to the nearest tenth of a foot? or in other words, the distance of the throw. So now we're really looking at a zero of the function. So we're looking at a zero, but way to the right. So instead of arrowing all the way over, I know it's probably, just by looking at their graph, it's between 70 and 80, and maybe we back up to 80, 86, something like that. Oh, that didn't like that at all. Not 86, 76. 76, let's see if it still works here. So yeah, 77.8 feet away. 77.8 feet, because it says to the nearest tenth of a foot. From what height was the shot released? Well, shots are released when X is 0. So those are 0, so 6.1 feet. The ball is thrown upward and outward from a height of 6 feet. The height of the ball, f of x in feet, can be modeled by that function, where x is the ball's horizontal distance in feet from where it was thrown. What is the maximum height of the ball and how far from where it was thrown does this occur? It's a very similar question. Actually, I already put this into Y2. Let's turn that back on. Let's turn this one off. Graph, and let's see. Yeah, our window is way too big for this now. 0 to, let's try 10 by ones. 0 to, I don't know, 15 possibly. I'm just guessing right now. Yeah, that's not too bad right there. What is the maximum height? So we can calculate a maximum. Here it comes. So there's certainly to the left of the maximum. There's to the right. Let's back up. 1.5, what is the maximum height? 1.5, let's see, measured, I think everything's measured in feet here. Feet, and then 7.8 feet away. How far does the ball travel horizontally before hitting the ground? Around to the nearest tenth of a foot. So again, that's going to be a 0, so we're going to calculate a 0. I'm going to arrow over. I'm looking at y to be positive. Nope, it went negative. Let's go back up. There's it positive. I'm looking for y to be negative. That's good enough. We can just back up a little bit. And that negative 1 e to the negative 12, that's actually a 0. So 4.6, how far does it? To the nearest tenth of a foot. So 4.6 feet. Graph the function that models the ball's parabolic path. We've done that. There it is. Among all pairs of numbers whose sum is 20, x plus y is equal to 20. Find a pair whose product is as large as possible. What is the maximum product? So the product is as large as possible. Well, let's get rid of one of the variables there. Let's go y is equal to 20 minus x. So let's plug that in over for this y. So the product now is x times 20 minus x. So the product is 20x minus x squared. Let's find the vertex of that function right there. So the x-coordinate of the vertex would be negative b over 2a, which is negative 20 over 2 times negative 1. The a is negative 1. This is the b. This doesn't have a c. So negative 20 over negative 2. So the x is 10. So when x is 10, we have the biggest product. So the other one must also be 10 because I know that they add to 20. So, but it says what is the maximum product? And the maximum product is 100 is the maximum product.